Back to our worksheet having to do with the work kinetic energy theorem, or at least that will play a role in the solutions. So we dropped a ball from rest at the top of a building. It falls a long distance, but in the first 400 meters, at the end of that time period, it has a speed of 20 meters per second, and it's very close to its terminal speed, so air resistance is not negligible during the motion. A asks, what net work is done on the ball during these 400 meters? And we can straightforwardly apply the work kinetic energy theorem to find the net work done by all forces on it, because we know its final speed is 20 in SI units and its initial speed is 0. We know its mass, so we can calculate the difference in 1/2 mv squared. And I should say these solutions were written in a different semester when we weren't using Ke to denote kinetic energy, but just K. So I've slightly different notation, but I'm trying to follow Giancali's notation now. So the final kinetic energy is 1/2 times the mass times the final speed squared. Initial kinetic energy, that's 0. It was going at 0 speed then. Crank those through and you get 100 joules is the net work that was done on it. What work is done? This is B. What work is done by gravity during those first 400 meters of falling? Well, I can't use the work kinetic energy theorem, but the gravitational force is constant, so I can use my old friend. The way to calculate work when a force is constant is just Fx times delta x, or if I aim delta y, my y-axis downward, then the force y component is just the weight force, and delta y is how far it falls. So Fy, if plus y is down, then Fy for the weight force is mg, 0.5 times 9.8, and delta y is 400 meters. Again, we're aiming our y-axis down, so I get 1,960 joules. C. What work is done by air drag or air resistance during these first 400 meters of falling? Here it seems like we might be out of luck because I don't know really much about the air resistance force. It's complicated. It's not constant because when I first release it, there's hardly any air resistance on the ball, but when it gets close to terminal speed after 400 meters, the air resistance is large. So it's not even a constant force, so I certainly can't calculate it using something like this. But I can calculate it in kind of a backward way by noting that there are only two forces acting here, the air drag force and the gravitational force. And so the net work done, that means work done by all forces, is equal to the work done by gravity plus the work done by air drag, and I can solve that for the work done by air drag in terms of two things I've already answered above. So when I take this difference, I get minus 1,860 joules. A negative amount of work is done by air drag or air resistance, and that's because it's being displaced downward, but of course the air resistance force is pushing back in the upward direction against the direction of motion. That's problem 3. Problem 4 says an astronaut twirls a 1.5 kilogram ball in a 0.7 meter radius circle at 3 meters per second speed, keeping the string fixed at the circle center. I demonstrated this kind of thing in class all the time, but if you imagine it happening in deep space, it really is uniform circular motion, so the speed's not changing. How much work does the string do on the ball? So the string force on the ball during 1/2 of a revolution. Excuse me. And the answer, somewhat surprising to some people, is that it's 0. And that's because, well, the string force is the only force on the ball, and therefore the net work done on the ball is the work done by the string on the ball. So I can calculate the work done by the string by the net work. The net work is equal to the change in the kinetic energy of the ball, and it's not speeding up or slowing down, and therefore delta Ke is 0, and that means that the net work is 0, and therefore the work done by the string, because it is the net work, right? There's only one force acting on it, is 0. Another way to think about this is that as the ball just goes through a tiny little change in position, it's moving in the tangent direction, whereas the force is acting on it in a perpendicular radial direction. And if the force is perpendicular to the displacement, it does a little bit of 0 work, and it does little bits of 0 work all the way around for that 1/2 revolution. The answer wouldn't be any different for 3 revolutions or a 1/4 revolution. I just put that in for definiteness. Okay, problem 5. 1,500 kilogram car moving at 25 meters per second suddenly applies the brakes and comes to a stop while moving 50 meters before it comes to a stop. Find the work done by the road on the car via friction during this process. So the road is pulling back on the car, it's actually stopping it. Again, we can apply the work kinetic energy theorem, the net work done, which is the work done by the road on the car. There aren't any other sizable forces that are doing work on the car. And so the net work is the work done by the road on the car, and that's equal to the change in the kinetic energy. Final kinetic energy is 0. Initial kinetic energy is 1/2 mv squared, and we get a large negative work in this case. And that's because the friction force is opposite of the displacement. Okay. The other forces, by the way, the normal force and the weight force, do 0 work because they're perpendicular to the displacement. All right, let's take a break.